Greetings and welcome to the introduction to astronomy. In this lecture, we are going to talk about space telescopes put up above the atmosphere for various reasons and to be able to look at objects in more detail. So let's take a look at what this is about. Why do we want to put telescopes in space? Well, one misconception is that it brings them closer to the astronomical objects. That is very definitely not true. Astronomical objects are so distant that putting a telescope in space, putting it up even a few hundred miles up above Earth, makes it no closer to a star than anything else. Moving 1 millimeter closer to a cross country trip really doesn't change your how far you have to travel to get across country. And that would be vastly overestimating how much the little bit of movement up above the atmosphere is in terms of getting closer to the objects in space. So really the reason is that only a very small part of the electromagnetic spectrum can get through our atmosphere. And we've looked at this previously. Most of the visible light and part of the radio waves. Those are the two types of telescopes we have looked at so far. However, gamma rays, X-rays and ultraviolet do not make it through the atmosphere. Much of the infrared is absorbed by the atmosphere. So there are a lot of regions that we cannot see from Earth's surface. Now, why do we do this? Well, again, we get a completely different view of the universe. And we've looked at something like this previously. This is the Crab Nebula. Here in the middle is visible light. We see the radio image. Those are the two that we've looked at so far. However, looking at things in other wavelengths such as infrared, ultraviolet, X-ray, and gamma ray can help give us a complete picture of the object by looking at it in all those different wavelengths. So any one of these does not give us a full picture of what the object is like. So it's not that visible light is bad, it's just incomplete because we're looking at only a tiny portion of the electromagnetic spectrum. So let's first look at some infrared observatories. In order to observe in the infrared, we need to get above water vapor. Water vapor is very good at absorbing infrared light. So we need to get above the troposphere, which is the lowest layer of the atmosphere. There are a number of ways this can be done, including using balloons and aircraft such as Sophia pictured here, which is an aircraft flies high up in the atmosphere to be able to observe infrared light getting up above that water vapor. We also can use things like spacecraft and spacecraft getting up into orbit. Again, we're getting up above the water, well above the water. And therefore we can use that to be able to see the universe in the infrared. Now, one of the key things with an infrared detector is that it needs to be kept very cold. So that's important because otherwise it would be emitting the light it is trying to detect. What does that mean? Well, remember, as a black body, everything gives off things based on its temperature. So something that is heated, such as a detector, would tend to give off infrared light. Now that would not affect a visible observation. However, so if your CCD is giving off infrared light, it makes no impact on your observations in the visible. But if you're trying to detect it, it would be like that CCD glowing in visible light, just bathed in visible light. And the little bit coming from the stars would be insignificant by comparison. So one of the keys with infrared detectors is that they need to be cooled to allow them to work properly. Now we can also put visible light telescopes up in space, and Hubble Space Telescope is one of these, launched in April of 1990 with a 2.4-meter mirror. So here we see Hubble. It's up above Earth's atmosphere, and it gets above the atmosphere, so there's no interference. And what that means is that we can get the theoretical resolution that we discussed previously and not have to worry about atmospheric seeing. In addition, some parts of the infrared and ultraviolet are visible as well. And that allows for a wider field of view to be able to look at things. Now you can't look at various high energy types of light like X-rays or gamma rays. They need completely different styles of telescopes. So a mirror will not reflect those. Now, when Hubble was initially launched, it was found that the images were no better than those taken from the ground. And that was great concern to everyone. And it turns out that there was an issue with the mirror that was ground incorrectly. So it was ground just slightly to the incorrect shape. In fact, it was a testing device that was out of position by a very tiny amount, 1.3 millimeters. So incredibly small amount, but enough to throw off that shape of the mirror, which meant that at first Hubble was no better than a ground based telescope. However, since we found out what the error was, we knew what that was, and we could make a correction then. And a future shuttle mission was able to adjust the optics within the telescope to allow to correct for this and give Hubble the beautiful crystal clear vision that we expected from it. Now we also can look at high energy. So some of the high energy observatories we use, things like the International Ultraviolet Explorer, which was up for nearly 2 decades to be able to study the universe in the ultraviolet, and the Chandra X-ray Observatory, and the Fermi Gamma Ray Telescope, again, to look at the universe in other parts of the electromagnetic spectrum. So X-rays and gamma rays as well. Now, one other space telescope to look at that has been launched is the James Webb Space Telescope, launched December 25th of 2021. This is much bigger than Hubble, 6.5 meter mirror as compared to the 2.4 meter mirror of Hubble. It looks at the universe in red and orange visible light and infrared light. So it can't see the entire spectrum. It looks at primarily the longer wavelengths here of red and orange and infrared. And it has a very interesting orbit in that it is out beyond the moon. So this shows a little bit about its trajectory as it was launched. So it was all the different separations, the solar array deployment, and so on as it traveled out to this distance out here at what we call the L2 or Lagrange 2 point, a stable point in the Earth Sun gravitational system. So it's out well past our moon and has since been able to give us some very nice images since the first images were released in July of 2022. So being able to see with far more detail than what Hubble had been able to. So here is an example of one of those images that we see. So this is an example of the image of that was taken of a deep field. So looking at a relatively empty part of space and taking a very deep image. Now you'll be able to note Webb images by the diffraction pattern going through them. And it's a little bit different than the diffraction patterns that you see going through the Hubble Space Telescope, which I'll look at in a minute. But here we see a 12-hour exposure for the Webb telescope. Now, the same field was imaged by the Hubble telescope, which took weeks, and we had this image. Now, if you compare, the Hubble image was amazing when we got it, and you can see the difference in the diffraction patterns there. But the Webb Space Telescope is showing far more detail and far more objects than Hubble was able to see. So you can see some objects that do not appear in the one do appear in the other. There are a lot of faint objects that were not visible to Hubble. So we expect over the coming years to get a lot of great science out of the Webb Space Telescope and improve our understanding of the universe and all of the objects that we study in it. So let's go ahead and finish up with our summary. And what we looked at this time was that the only light that gets through is the visible light. and radio waves. Those are the only two that penetrate Earth's atmosphere and can be seen from the surface. Yes, you can do some infrared, but for the most part, this is what you can observe. Space telescopes give us a new view on the universe and can observe without having to look through the distorting effects of Earth's atmosphere. And there are still future telescopes that are planned that will again improve this, with James Webb just having been launched uh, not all that long ago. So that concludes this lecture on space telescopes. We'll be back again next time for another topic in astronomy. So until then, have a great day, everyone, and I will see you in class.